Now we're getting into a new chapter, chapter 20 in your book. Deals with what we call electrochemistry, and that is how there are certain reactions that we call redox reactions, which we'll get into in the next lesson, in which there's actually two reactions, we call them half reactions, in one reaction. One is the oxidation reaction, the other is reduction reaction. That's where the term redox comes from, redox. And in order to understand how this works, we have to understand that electrons are very easily removed. We talk about this a lot in physics, and in Chem 2, this is the same kind of thing, where electrons are rather easily removed or absorbed depending upon what the conditions are. In this case, the transfer of electrons, instead of being a charge like it is in ionic compounds, we haven't really discussed that at all in covalent compounds. And while this is true for both ionic and covalent compounds, this is especially true in covalent compounds because people don't associate charges with covalent compounds outside of the polyatomic ion thing. But within the polyatomic ion, we have a series of ability to transfer electrons in at least one of the elements within the polyatomic ion. And so we call that ability to add or remove electrons oxidation numbers, and it describes the number of electrons that can be removed or added to it. And this is an example right here. You take an iron atom and you can change it to an iron to positive ion by removing 2 electrons. Now that's nothing earth-shattering. We've done that since we talked about ions. But this is the same process that can also occur with covalent substances as well. Copper positive, and by the way, because we are giving up 2 electrons, and the fact that the oxidation number, which we'll talk about this a little bit, goes from 0 to positive 2. This makes this an oxidation reaction, and we'll get that, like I said, we'll get that more heavily in the next lesson. And then but the counterbalance to it is the reduction reaction. And the reduction reaction, those electrons are being given up, are being absorbed by another substance, in this case copper 1 positive ions, that will absorb that electron and create copper metal. This is the basis for batteries. This is how batteries operate. One part of the battery gives up electrons, but then we take a wire and reroute the electrons away from that reaction and pass it through some kind of what we call resistor or some kind of mechanism to make it do the work, like a phone or a Game Boy or whatever, and then pass that back on to the original battery as what we call a ground, to allow the flow of electrons to be absorbed by something else. We have to have both these reactions in order for the overall reaction that we are looking at to have to occur. So I know it sounds a little complicated, and we're going to break it down. Of course, I'm doing the best I can to break this down. And this is really one of my favorite areas because we're not dealing with complex math in this particular chapter. There is math, but it's not that complex. It's just a little bit of algebra to kind of keep your mathematical senses alive. There are certain rules for determining oxidation numbers. And again, this isn't going to mean a whole lot to you, but as we get through the 4 examples I'm going to do for you, this is going to make a lot more sense. But you need to refer to this listing of options here in order to do the problems, the 5 problems that you're going to be doing for the practice problems for this. First of all, any atom that is not combined with another atom, or I should say element with another element. The atoms of an element, you don't see atoms of other elements with it. It's just by itself, whether it's in singular form or diatomic form. All those atoms will have an oxidation number of 0. There will be no charge for them. Well, I shouldn't say charge, because charge is not what oxidation number is. But if we were talking ionically, it is the same thing, but covalently it's not the same thing. So we've got to be careful of that. When you have oxygen combined with something else, it's always going to be -2, just like its location on the periodic chart. Group 6A is -2, it goes to charge. the oxidation number is also -2. But there is, well, actually 2 exceptions, but only one that we're going to deal with, and that is called the peroxides. And peroxide is a polyatomic ion that we've ignored until 2 lessons from now, and then we're going to take it up. But that oxidation number for a peroxide is -1 for one oxygen atom. Okay? Hydrogen, that is in a group of elements that has at least one other nonmetal, that hydrogen will always be +1. And virtually all but a very small handful of compounds that we will be dealing with, hydrogen will always be +1 unless hydrogen is by itself, in which case then it's 0 because it's diatomic by itself, and according to the rule number 1, that would be 0. But if hydrogen is combined with a metal, then its oxidation number is -1. That now becomes an ionic compound, and it'll always be negative when it's with a metal, which it has to be positive. And remember, in number 4 here, this is an important one. The sum of all oxidation numbers in a compound has to add up to 0, which explains why hydrogen with a metal has to be -1 because the metals are always positive. And then the last one, which is also a pretty big one, if it's not a compound, if it is a polyatomic ion instead, then the sum of all the oxidation numbers has to equal the charge of that polyatomic ion. So we're kind of getting more into the weeds as to how electrons are able to move about with now covalent as opposed to just ionic, which is what the only thing we dealt with up to this point. Now we're going to get a much more full look at how these compounds work. So let's take a look. What we're going to do in the assignment that you're going to get today is that I'm going to give you 5 redox reactions. And you're going to be asked to find the oxidation numbers for each one of these. And so you always go with the ones that are the easiest first, then build from that. The easiest one is this one right here. This is a single element with an ionic charge of +3. And because it's ionic, it's also going to have an oxidation number of +3. So I'm going to put +3 right there and circle it. And when we do oxidation numbers, this is how I'm going to want you to do. I want you to identify the oxidation number and circle it so it doesn't look like a charge. And that becomes really important later on when we start doing the next 2 lessons, which deals with balancing redox reactions. All right, so we got that. Now we come over here, and here's carbon dioxide. Now, rule number 2 says combined oxygen is -2, except peroxides. And we're not going to deal with peroxides until we get to the second of the redox reaction lessons. So we know that oxygen is -2. So we're going to treat this like a little algebra problem. We don't know what carbon is, but we do know that oxygen is -2, and we got 2 of them. So 2 times -2. And this is a compound, which means it has no charge at all. So the sum of the oxidation numbers has to add up to 0. So when you do the algebra, this becomes C minus 4 equals 0. And 4 to both sides, C is equal to +4. Now I kind of insist that you put plus and minuses for oxidation numbers. Even though +4 or +4 and 4 are the same thing, I want to emphasize the fact that we are going to have positive negatives, and it's going to have an effect upon your arithmetic in this whole scenario. So that means oxygen here is -2, and this carbon here is +4. Okay, so now we're going to come over here. We have Cr2O7 and with a total charge of -2. Now again, we know that oxygen is -2 when it's combined with something else. So we just go ahead and put that up there. But now algebraically, we're going to write it this way. We're going to have 2 times Cr plus 7 times -2 equals, now this is not a molecule, this is a polyatomic ion. And according to the last rule, the sum of all the charges, or sum of all the oxidation numbers, has to add up to the charge of -2. So this becomes 2Cr minus 14 equals -2. So we add 14 to both sides. That means 2 CR equals 12. Divide both sides by 2, and CR equals positive 6. So we'll put a plus 6 right there. Over here, same kind of thing. We know oxygen is -2. So we have 2 times carbon plus 4 times -2 equals the total sum of the oxidation numbers, which is -2. So we rewrite that as 2C minus 8 equals -2. Add a positive 8 to both sides. 2C equals 6. Divide both sides by 2. C equals positive 3. And there you have it. And even though we have some redundant oxygens in there, I still want charges above every single atom or element in each substance. So just because we have -2 over there doesn't mean we don't put it there. We have to put it everywhere there's an oxygen. So this is the format I want you to use.